Alright, hello everyone. Today we're going to have a look at differential equations. So, the study of differential equations began in the 1600s with Isaac Newton's investigation of the orbits of planets around the Sun. Now, he referred to these equations as fluxational equations. And the term differential equation was suggested by a contemporary of Newton, which is Gottfried Leibniz, who is a very famous person who helped in the development of calculus, and he did much of the early work on them. So a differential equation is an equation that relates some unknown function, differential function, to one or more of its derivatives. So for example, the general form of a first order differential equation could be y1 is equal to f of y, f of t, y of t. So here we can see we're expressing the rate of change of the quantity of t in terms of two variables, time t and the quantity itself. But that sounds a bit complicated. To shorten that, in a nutshell, a differential equation is an equation that involves a derivative. So for example, we've got y dash equals minus 7y, or x squared y dash dash minus xy dash plus y equals 0. Or we could say, instead of y dash dash, we could say down here, we've got d2y to x squared minus 2x to y dx plus lambda y. All of these are examples of differential equations. They're equations that, instead of just being, say, y equals x or y equals ax squared plus bx plus c, we're involving the differentiation somehow. And obviously we're going to work a lot in this topic with differentiating, but more importantly with integrating. So the order of a differential equation is the highest derivative that is involved in the equation. So for example, an equation whose highest derivative is y dash would be a first order differential equation, whereas one with the highest being y dash dash would be known as a second order. Now notice that all of the equations above only have y differentiated, or just the x differentiated, but not both. Now we can actually differentiate with respect to both x and y at the same time, and these examples are known as multivariable equations, and the study is multivariable and multivariable calculus. So a multivariable equation is just an equation which is in terms of two different variables. So we could say f of xy is equal to x squared minus xy minus y. It's an equation that's involving in two variables, and it's equal to a function of two variables. So differential equations involve multiple variables. Introduce this cute new symbol, which from my experience, it's extremely hard to draw, especially when you've got one question involving this new symbol and another question involving normal differential equations. So it's really just the Greek letter for D, I'm pretty sure, that we use, and the study of this, which is the calculus of equations involving more than two variables, is called partial differential equations. We'll never see it in high school maths, but you will see it. It's the basis of all practical-based math subjects at university, like in engineering. So here, instead of dy dx, we've got the partial derivative of du to t. So we've got partial derivative. So we're differentiating an equation that involves u, and it might involve something else. It might involve x as well, and we're differentiating both of them at the same time. So that's a bit of a sidetrack to some university maths. Today, and in Extension 1 and Extension 2, but in the Year 12, any mathematics courses, we're just dealing with differential equations, not partial differential equations. So we're going to state whether these are differential equations, and if they are, we're going to state their order. We might just talk about these. So example number 1, yes, it's a differential equation. Why? Because it involves a derivative. We've got to state its order. The highest is y dash dash, so it's order 2. Part B, no, that's not a differential equation. It doesn't involve a derivative. It's an equation, but not a differential equation. Part C, y dash is x squared plus 1. Yes, it is a differential equation. It involves a derivative. We would have seen this in the past to say dy dx equals x squared plus 1, and we can solve it by integrating to get y. And part D, y is equal to y dash 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 dash. Yes, it involves a derivative. Its order is 4. Now, we're mainly going to be dealing with first order differential equations, and in a few instances we're going to deal with higher order differential equations. Most of the time, rather than actually learning how to solve them, we're just going to verify whether certain things can be solutions to these higher order differential equations. We will briefly deal with second order differential equations, but not in depth, because it can get very tricky. So the solutions to differential equations, well, they're equations and they do have solutions. So the solutions are not just numbers, but functions of x, or more generally, there might be a relationship in terms of x and y. Now we can test whether a function is a solution by substituting it into the differential equation. So test whether each function is a solution to the differential equation y dash is equal to minus 7y. So, two ways of doing this. Number one is to integrate this equation and see if we can somehow get this. And number two is to differentiate this and see if it satisfies this. So I might differentiate, that's usually the strategy that we use. So y dash is equal to 7 times by 20, 20 times 7 is 140, e to the 7x. So we've just differentiated that, and we know that y is equal to 20 e to the 7x. So this could be expressed as 7 times 20 e to the 7x, which is equal to 7y. So therefore, no, it is not a solution to the differential equation because we don't have a negative out the front. Part B. We're going to differentiate that. We get y dash is minus 7 times by 20 e to the minus 7x. Now 20 e to the minus 7x is y, so this is a minus 7y. So therefore, yes, it is a solution to the differential equation. Show that y is tan x is a solution to the differential equation y dash is equal to 1 plus y squared. Well, y dash, if y is tan x, is equal to sec squared x. Now we do know a certain identity, that 1 plus tan squared x is equal to sec squared x. So let's go y dash is also equal to 1 plus, well, y is tan squared x, so tan squared x, which is equal to sec squared x. So therefore, yes, it is a solution to the differential equation. Now, indefinite integrals are equivalent to differential equation. So an indefinite integral such as the integral of 2x dx is actually saying find a function whose derivative is 2x. So it's the equivalent of saying y dash equals 2x. So to solve a differential equation, to find the value of y, or to find the function of y, we're going to integrate. Okay. These are two very, very important concepts that we're going to learn, the general solution and a particular solution. And I can tell you that those two words, general solution and particular solution, are humongous concepts in university, and I really, really wish that they were part of the syllabus I learnt at school. I was the last year of the old syllabus. So the general solution to a differential equation, when we integrate functions, we always get an arbitrary constant that's added to the equation. Now, since this constant can take any value, we call the set of possible solutions, which is an infinite number of solutions, a family of solutions. Now, this form of a solution is known as a general solution. Now, in our differential equations, a general solution it's not always just simply plus c. It's not just plus some constant. It could be, but not all of the time. It may be the coefficient of a particular term in our solution, could be our constant. Now, the order of an equation will determine how many arbitrary constants the answer will have. For example, the general solution of order 2 may have 2 arbitrary constants in the solution. Now, this begs the question, how do we know where the constant goes? It's a good question. We don't. Often what we do is we analyse the question and guess the most generic solution and apply conditions of the equation to find the correct solution. So here are some common guesses. So if we've got a constant, our guess is going to be a, because if you integrate a constant, you get a function, just x. If you've got 5x plus 7, we might guess ax plus b. We can do these types of guesses, and we're going to guess what is the most general form. So number 5, sine 4x. Well, the solution could have involved causes, and the coefficient of cos is just 0. These are what we call, they're our guesses to our differential equations. Now, the reason I'm showing you this is because this is what you will do in university. Unfortunately, you will not be required to know this in Extension 1, apart from when we learn something known as the logistics equation, which is just simply this guess right here and here when we're looking at exponential growth and decay. Often, though, they'll just give it to you. So number 4, we're showing that y is aex minus x minus 1 is a solution to the equation y dash equals x plus y. Now notice, the constant in this is not just a plus c at the end, it's an a here. So to have a go at doing that, we're just going to differentiate this. So y dash is equal to aex minus 1. And we're trying to show that this satisfies this equation here. What we might do is go ahead and substitute this into here. So y dash is equal to x plus y, which is aex minus x minus 1. Our x's will cancel and we get aex minus 1. Therefore, y equals aex minus x minus 1 is a solution. Example 5, we're going to show that y equals sine of 7x and y is cos of 7x satisfy this differential equation. So it's looking like that this differential equation has multiple possible solutions, and we're going to learn that that is the case. It's a family of solutions that can satisfy this equation. So y is equal to sine of 7x, y dash, that would get us 7 cos 7x, and y dash dash would get us minus 7 sine of 7, not minus 7, minus 7 times 7, which is minus 49 sine of 7x. Now sine of 7x was y, so it's minus 49y. Okay, that's half of part A done. Let's do y equals 7, cos of 7x. Well, we differentiate cos, and we get minus sine. So it's minus 7 sine 7x. Differentiate that again to find y double dash. We get minus 49 cos 7x, which is minus 49y. Okay, we can do that. Part B and C I'm going to skip for this video. We're just doing the same thing, and we can show that these are solutions to the differential equations. Okay, the other concept in today's video is the notion of the particular solution to a differential equation. So the general solution of a differential equation is kind of like our family of solutions. It's the solutions with our constants in them. A particular solution is a solution that goes through a certain point on our Cartesian plane, and we're going to learn and represent how to graph that in the idea of slope fields. But a particular solution is really in advanced when we're just finding what the value of that constant c is at a particular point. So general solution is the solution in general. Particular solution is one of those infinite amount of family of solutions. So we saw, especially in motion and rates, that arbitrary constants in the general solution can be evaluated provided we have a suitable initial condition or a boundary condition. The resulting curve is known as a particular solution, and the problem of finding particular solutions to a differential equation and a suitable initial conditions is called an initial value problem. And there also may be restrictions on variables. For example, time has to be greater than 0 could be a restriction that we might want to consider. So example 6 is we're solving this differential equation, and given that 2, 7 lies on the curve. Really what we're doing is we're solving dy dx equals 2x. So to solve that, so y dash equals 2x, we're going to integrate both sides. So the integral of y dash is y, and the integral of 2x is x squared, or 2x squared on 2, and the 2's cancel, plus c. Now we're told that 2, 7 is a solution, so we substitute that in. 7 equals 2 squared is 4 plus c, which means c is 3. So therefore a particular solution is y is x squared plus 3. So that is a particular solution to this equation. Now the plus 3 isn't the particular solution, the whole equation is the particular solution. Okay. In a previous example we showed that that was a general solution of y dash equals x plus y. Part A, find the particular solution passing through the origin. So all we're doing is we're going, okay, 0 is equal to a e to the 0 minus 0 minus 1. Of course, that means a is equal to 1. So we're substituting in the point 0, 0. So therefore, a particular solution passing through the origin is x minus 1. Now we can do all of that. Parts B and C, we're just going to do that same process again and again, except we're substituting in minus 2 and 0 and minus 1. Okay. Higher order differential equations. So an initial condition is usually given as a point on the curve. For higher order differential equations, however, the initial condition may also involve a point on the graph of its derivative, that is, a value of y dash for some particular value of x. For two arbitrary constants, we need two initial conditions, which usually form two simultaneous equations. So we showed in work example 5b that y equals a sine 7x plus b cos 7x is a solution to the equation y dash dash equals minus 49y. Find the solution, find the particular solution for which y0 is 1 and y dash 0 is 14. Okay, to satisfy and to solve this equation, well, we're first of all going to use our initial condition, which is this one here. When y is 0, when x is 0, y is 1. So 1 equals sine of 0 is 0. So b, now cos of 7 times 0 is 1. Cos of 0 is 1. So 1 equals b. Now we need to use our second initial condition, which is y dash 0 equals 14. So y dash in this particular equation is going to be 7 cos 7x minus 7b sine 7x. Now we know b is equal to 1, so we're going to replace that with 1 there. And we're told that this is equal to 14. And I've actually missed out on a little a. This should be 7a cos 7x. Now we're making x equal to 0, so this is 7a because cos of 0 is 1 and sine of 0 is 0, so that goes away. So that means a is equal to 2. So therefore the particular solution to this equation given these conditions is y is 2 sine 7x plus 1, which is b, cos 7x. And that is our particular solution to this particular question. Now, relations can also be a differential equation. Relations, remember from our work in advanced maths, are equations that are not functions, such as a circle. Now, the way we differentiate relations is something you would have never seen before, and it's something that used to be in the old Extension 2 syllabus. However, it can be beneficial to know the idea of implicit differentiation. So, implicit differentiation enables us to differentiate one variable with respect to another. So, for example, if we wanted to find d by dx of y squared, we would use the chain rule. We would differentiate y, we get 2y, and multiply it by dy to x, and that's because those dy's there will cancel. Or if we want to differentiate xy with respect to x, we're going to differentiate x, which is 1, times it by y, and then plus the differentiation of y with respect to x, which we don't know. That's what we're trying to find, and times it by x. So differentiate the equation x squared plus y squared equals a squared of the circle with respect to x, where a is greater than 0, and show the equation of a family of curves satisfies the differential equation y dash equals minus x on y. So we've got x squared plus y squared equals a squared, and we're going to differentiate this. Normally in advanced differentiation, you would have to make y the subject to do this, but we don't have to. To differentiate with respect to x, we're going to differentiate first of all x with respect to x, which is 2x. And to differentiate y with respect to x, what we're doing is we're going to differentiate y, which is 2y, but multiply it by dy dx. No, sorry, we're going to multiply it by dx dy, I think. D by dy times dy to x. No, dy to x, sorry. And if we differentiate a, we get 0. So 2x plus 2y to x is equal to 0. And we just have to make dy to x the subject of this, because that's what we were trying to do. So dy to x, 2y, is equal to minus 2x. The 2's will cancel. We can divide by y, and dy dx is equal to minus x on y. So to recap what we've done, to differentiate x squared plus y squared equals a squared using implicit differentiation, we're going to differentiate x normally, differentiate y normally, but then multiply it by dy to x to account for the fact that we're differentiating with respect to x, not respect to y. We then make dy dx a subject because we're trying to find a differentiation. Now dy dx is another way of saying y dash. So that's equal to y dash, and we're done what the question was asked us. So we've shown that it is a solution to the differential equation. Okay, part B, do I have more space? I do. Part B, differentiate xy equals a squared of a rectangular hyperbola with respect to x, and show that this equation satisfies the differential equation y dash equals minus y on x. So we've got xy equals a squared. We're going to use the product rule here. The product rule tells us we differentiate the first thing, which is 1. We differentiate x and get 1, and times it by the second thing, y. Plus, the differentiation of the second thing is the differentiate y, we get 1, but we have to multiply it by dy to x, because we're differentiating with respect to x, and then we multiply it by the first thing, x. Differentiate a squared, you get 0. If we make dy dx the subject, we get dy to x equals minus y. Divide by x, we get dy dx equals minus y on x. And dy dx is just y dash, so y dash equals minus y on x, which is what we're asked to prove. Done. Okay. The last concept I think yet in today's lesson is first order linear differential equations. So a first order differential equation is known as linear if it can be expressed in the form y dash plus f of xy plus equals g of x. So y dash plus something times y equals a function of x. So y dash equals a function of x times y, which is equal to some other function of x. So for example, here are some first order linear differential equations. Something important to note is that these things to be linear, they don't have to involve x, but they can be functions of x, but they can't be functions of y. So this could be 3, or it could be 3x, but it couldn't be y or 3y. So here are some linear differential equations. We can see these all involve y times by some function of x. Y times some function of x. Y times some function of x. So here we've got y, y dash. This one's in the wrong order, but it's still a linear equation. So classify these differential equations in terms of their order and whether they are linear. First of all, they're both of order 1. They're first order differential equations because the highest differential is y dash. Now, if we have a go at simplifying this, we're going to get y dash x minus y equals 0. Let's see if that's allowed. Y dash x. So, yes, this one is linear because we've got y dash multiplied by something, and then there's a function of y. There's a y, and then there's equal to 0. So, yes, this is linear. Let's have a look at part B. If we simplify this, we're going to get y dash y equals x, or y dash y minus x equals 0. So that is, no, this is not linear, because we're not allowed to have a function of y multiplied next to the y dash. We can see in all of these examples, there's no y next to any of the y dashes. They're all functions of x. Okay, that's an introduction to differential equations. Thanks for watching.